kind of stuff. Muted. Yay! So we did talk about linked lists and vectors, and then stacks, queues, dequeues, and priority queues. Talked about linked lists, vectors, and which one tends to be faster? Linked lists or vectors, right? First, because get is actually constant rather than linear, and then because locality of reference. But some of you will probably end up comparing linked list versus vector and seeing what happens. You will tell me whether it's actually faster or it's bunk. Maybe we'll do a heap. We started talking about trees, and sorry, you can see where my efforts on creating nodes stopped. We have binary search trees. Where we would have a node in general containing a key and a value. If you're doing, for this stuff, it's almost the same to implement a set versus a map. The only difference would be that if you're doing a map, you're attaching a value to a key, so you have to store the value. If you're doing a set, you would only be storing keys. But sometimes the data structures become slightly different. Our nodes tend to be binary for the simplest ones. So those are the ones we implement in memory. Those are the ones you see in data structures, right? And it is a search tree because the left and right nodes depend on the key. So usually anything on the left is lower than the key in the current node. Anything on the right is higher than the key in the current node. Does that idea make sense? Yes? No? Maybe? You have seen binary search trees? Reasonable enough? Yes? Cool. What's the order of operations on a binary search tree? How long does it take to search? Log n, right? If you have n elements in the tree, you do log n. What does that mean? Amazingly fast, right? If you have 1,000 elements in the tree, about how much does it take you to search? 10, right? Which is log of 1,000. If you have 1,000,000, how much is it going to take you? 20. If you have 1,000,000,000, an American billion, how much is it going to take you? 30, right? Every 1,000, you just do 10 more, right? So it's a factor of 1,000, right? And you just add 10. It is amazingly cool, right? How about insertions and deletions? If your balance tree is if your binary search tree is balanced, right, and it's red, black, or 2, 3, or something like that, how long do they take? Not n, log n again. You're only touching the path, the search path, basically. So you're only touching nodes within the search path. So only those nodes would need to change. So it's still log n. Does that idea make sense? That makes trees amazingly fast, right? Or balanced trees amazingly fast. how much extra memory are we using?
So it's basically a linked list except for each node points to
Yes.
So is that double?
So it's basically 2 pointers per object,
Yeah.
right? In a way, every object would have 2 pointers attached to it. So it's 2 pointers per object. Is that a lot or a little?
I guess it depends on your circumstance.
Depends on what.
What you're comparing it to?
Well, but depends on the size of the object,
Yeah.
right? If you're storing ints, then that's triple the size of an array of ints, right? If your objects are huge, then this is nothing. Does that make sense? So relatively, it depends on the size of the object. But it makes everything log, which is amazing. Can we do better? Well, actually, let me mention one thing, and they're actually B trees, and B stands for balanced, are actually multi-ways, so more than 2. And it happens that the algorithms are actually easier to understand many times. How does a B tree work? In fact, one of the balancing is 2 3 trees are basically B trees, and then red black trees are basically B trees. The idea is that at least insertion is very easy to understand. You're going to have, in this case, right, we have 4 keys and 5 values in this figure. Does that make sense? And there is different variations of the rules, but the rules for a B tree usually say your nodes are at least halfway full, other than the root. The root may, because if you have only or if you have only one element, then you're going to have a node with one element. Other than the root, your nodes have to be at least halfway full. And that guarantees that at most you search twice the log, right? If they're only halfway full. Is this much better than binary?
Depends on how many numbers you put in the node.
Like, if I put 1,000 in a node instead of 4, is that much better than binary? What does much better mean? If I put 1,000 nodes, right? How many would it take me to search for 1,000? Oh, well, order of 1, that's not true actually. I need to search and do things in them. But how about 1,000,000? Two. 1,000, each one of them has 1,000, right? How about 1,000,000,000? 3. How about 1,000,000,000,000? 4. Versus what happens in binary. If I'm using a binary search, I'm doing 10, 20, 30, 40. Versus 1, 2, 3, 4. Is it much better? Well, it's 10 times better, but it's a constant factor, right? It's not this awesome improvement. Does that make sense? It's about the same. Why? Because logs are related that way, right? Do you remember your calc? Rules for logarithms, right? Basically, there's a constant factor that relates the logarithm in one base to another. Just multiply by a constant, and you will always change the base. Now, how do B trees work? When I'm inserting, right, I find out where to insert. If I'm trying to insert, say, 13, I would insert it here next to the 12, right, on the thing in the middle. And life is good, I just insert it, right? What happens if I want to insert 3, the number 3?
It's going to take 6.
It's gonna try to put it here, right? And that node is already full. So what do I do?
Create another leaf.
Well, I do create another leaf, right? At what level? Not under it, because that would make my tree unbalanced. That would make my tree grow badly, right?
It wouldn't make it unbalanced because you only
Well,
get a factor of 1.
If I keep doing it, it would make it unbalanced.
Yeah.
What I do is add one more node to the parent. So in this case, I would probably have the number 3 pointing to 2 leaves, one with 1 and 2 and one with 5 and 6. Actually, depending on what I'm doing, right? Depending on what I'm doing, I may have, I may store the actual data in different ways. But assuming that I'm just doing a set rather than a map, I would insert the number 3 onto the root, pointing to 2 new leaves, and now I have 4 leaves on level 2. Does that make sense? Eventually, what might happen is that the root is full, and then I need to create a new level, but B trees grow at the top rather than at the bottom. Does that idea make sense? If you ever have like a week to spend on fun stuff, implement B trees. They're actually a lot of fun. They are sometimes too interesting, but a lot more fun than red-black trees. But does this idea make sense? They're actually easy to implement in a way. Red, black, and 2-3 trees are variations on B trees, except that in a 2-3 tree, it's actually not binary. You either have 2 or 3. And so it's basically a B tree with a level of 3. And that's one of the. In red, black, it ends up being the same, except that the black nodes are the 3rd element or something like that, and they're just inserted. One of those things. Something like that. ABL trees are slightly different. But I find B trees actually easier to understand how they work than the balancing for red, black, and those guys. So B trees are really cool. They don't give me anything better than logarithmic, right? Does that make sense? Can I do better? The answer is yes-ish. If I have an array rather than a map, right? How can I do it? If my keys were ints, what could I do? Actually, in my example, my keys are ints, right? So how can I do it better? Sorry? Hash table, but if I only have ints, right, what can I do? If my keys are going to be 32-bit integers, right, how can I do it so that the access is super fast? Sort them is okay, but it's actually log n still, right? Because I need to do binary search on the sorted thing, right? How can I do it so that it's blazingly fast?
You're talking about implementing this as an array?
Like, imagine that my problem is, yes, but imagine that my problem, right? My problem is map a value to each one of 2 to 32 ints, right? I only have my keys can only be integers from 0 to 2 billion or so. What can I do? Yes, just have an array of 2 billion elements and store stuff in there. right? If I do that, how fast is it? Blazingly fast, constant, right? Really, 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 really fast. What's the problem? Memory, right? So what can I do so that I get something as fast as the array, except that I don't use that much memory, right? If you think about it, right, the array would be the fastest thing. Well, trees are okay, right? But what else can I do? Hash tables, right? What are hash tables? Well, what I'm gonna do, imagine that I have okay, imagine that I having, let's put it in decimals, right? My keys can be numbers from 0 to 999,999, right? From 0 to 1,000,000 minus 1. Does that make sense? I could generate an array of 1,000,000 elements, right? And store stuff there. If it's null, then there's nothing there. If it's not null, then there is stuff there, and it's blazingly fast. But I need 1,000,000, right? Imagine that I know that my map is only going to have 1,000-ish elements, right? What can I do to store only 1,000 instead of 1,000,000?
You could make an array.
Array of what?
Buckets.
An array of 1,000, right? And then what do I do? Well, I divide each number by 1,000, right? And map it to that element, ish. What's going to be my problem? Well, I'm going to have collisions, right? If you happen to insert 1,000, 2,000, 3,000, 4,000, 5,000, right? It'll all be good. If you happen to insert 1,001 and then 1,050, right? Then I have a collision and I need to do weird stuff. Does that idea make sense? What is the easiest way to deal with weird stuff?
Salting. Go to the next one.
Salting, well, yeah, there is different ways of chaining, right? Either, to me, the simplest one conceptually is this. Instead of storing one element at the bucket, right? In hash tables, we call it a bucket. So you apply a hash function, in my example, divide by 1,000, right? And that gives you the bucket. And then in the bucket, what you can do is store a list of elements. Does that make sense? And then that's how I deal with collisions in the simplest possible way. Your implementation for hash tables, in this case, is super simple, right? Just apply the hash function, go find the bucket, and then do a linear search in there, right? Probabilistically, this is good, right? Because if you only have 1,000, elements, right? What are the chances of you having, for any given element, what are the chances of having a collision? 1 in 1,000, right? So for a hash table with 1,000 elements, if your keys were equally distributed, which is not guaranteed, right? You may have 1 or 2 collisions, right? So for 1 or 2 elements, you have to search twice, or search a list of 2. For all of the others, it is blazingly fast. Isn't this cool? I mean, even for the ones where you have 1 or 2 collisions, it is still blazingly fast for some versions of blazingly. Does that idea make sense for hash tables? So then you get into the devil's in the details, right? All of the details, right? There's a few things. First of all, how do you come up with the hash functions? first you map something to an int, and then you map that into your buckets, right? There is universal hash functions and ways to come up with those different ways, right? Then, what do you do with collisions? Well, I keep inserting, but at some point in time, right? If my hash table has only 1,000 buckets, and I'm gonna put 1,000,000 elements, right? My hash table is gonna suck, right? So what do I do? Increase the size of my table, right? So it will suck less, right? And play with my probabilities so that now I have less probability of a collision, right? How fast is increasing the size of my table? Sorry? Double what?
1,000.
Double the number of elements in my table, right? It's the size, not the number of elements, but, right? They are reasonably close. So it takes, right? Searching takes order of 1. Insertion usually takes order of 1. I just go put it there. But sometimes it takes order of n, which is horrible. Does that make sense? Amortized over all the insertions is order of 1, just like with the vector. My worst case scenario is order of n for basically everything, for searching, for inserting, for everything. But my average and amortized is order of 1. So when it works, it's blazingly fast. When it doesn't work, oh well, it doesn't work. Does that make sense?
So are the buckets generally sorted or not? Or it just depends on your implementation?
There is hundreds of different ways. Usually, I would say no, but it depends. Another thing says rather than actually store a list, just go to bucket plus 1. Just go to the next bucket and see. Then just go to the next bucket and see. There is actually a cool thing which I think is cuckoo hashing, which is, well, you have a table of 1,000 elements, right? And you are doing stuff with modulo or something like that, right? What you do is, rather than having one hash table, you have 3 hash tables. One of them is size 1,000. Another one is size 1,017, something that is prime with 1,000, and the other one is 1,329 or something like that, right? So that if there's a collision on the first one, you try inserting on the second one. And they are not related at all, right, with the hash functions and things. You use a different hash function so that, and then if there's a collision on that one, you then insert on the third one, right? And so if the chances of the first one getting a collision is 1,000, chances of getting a collision on both the first and the second are 1,000,000, and then the chances of getting a collision on 3 of them are 1 in a billion, right? Which means don't worry too much about it.
What is that method called?
Cuckoo hashing, I think. I may be confusing names and things like that. And I have some papers on the site if you are interested in basic idea of cuckoo hashing is to resolve collisions by using 2 hash functions instead of only 1. So there's variations on cuckoo hashing. When it works, hashing is amazing. Doesn't always work. If hashing is amazing, why do we use trees? Sorted is one, right? In a hash table, you have no way of finding a range, saying from 10 to 20. because 10 maps to one bucket, 11 maps to another bucket, right? With a tree, you can just say, oh, right? Kind of the nodes are sorted-ish. And so it makes it really to do range queries, to do sorted stuff. What's the other thing that trees have as an advantage over hash tables?
It doesn't repeat.
Sorry?
It doesn't repeat.
Doesn't repeat?
Like the values can't repeat.
In a hash table, they can't repeat either. Depends on how you implement.
Your
But-
worst, as long as it's balanced, your worst case and main
Yes.
case are always the same.
Your worst case is log n. What's your worst case in a hash table?
Yeah.
N. Right? So hash tables will have some poor thing that sucks, right? So one insert in your database sucks, and then everything else is fast. And then another insert happens to suck and everything else is fast, right? That kind of stuff. Does that idea make sense? We used to, in fact, most databases use trees, right? Relational databases use mostly trees for your indices. We now have kind of hash table kind of databases. Redis is basically a hash table in memory, and it's a database-ish thingy. There is tons of stuff both on better hash tables and on how to deal with that increment, right? Well, yes, it's going to take order of n to insert, but maybe what I can do is just put it temporarily in a place, start the insert in a different thread, right? Return yes, and you don't care what I'm doing, right? So when I'm done, I will make that the new version of the database or whatever, and then you didn't know that it took me forever. Because on average, amortized, it takes very, very little. Does that idea make sense? In memory, what do we use most of the time? Both. Do you use maps? When you use a map in Java, what do you do? A set. Have you used maps or sets recently? What do you do? You normally end up doing hash map or is it tree map? So you can either use hash map or tree map. And that will be both, and the same thing with sets. And those are also things that you can compare for assignment 2 and figure out the times and why are these things working, and then go look at the documentation, which version of hashing did they implement, all of that stuff.
Just off topic question, what is Java, what is this website?
Oh, Java REPL?
Yeah.
It's a REPL for Java. REPL is read eval print loop. When you're learning a programming language, having an interpreter is really cool. It's basically an interpreter, so it's a reads whatever you type, evaluates it, and prints it, and does that in a loop. That's a REPL. When you learn Python or Scheme or Prolog or something like that, you're always in a REPL. With Java and C++ and C, you tend to compile it, so it takes forever between when you type and when you get feedback. There is now tons of REPLs for every language under the sun. Java REPL is for Java and it's on the web, so you don't have to think too much. The session dies, you're not going to use it for big projects or anything like that, but for quick and dirty stuff, I don't have to go install anything. I just open Java REPL and go do it. If you use C# or .NET, LinkPad does the same for .NET, and it is amazing. The Java is now gonna have JShell, which is a REPL on Java 9, except that Java 9 is probably gonna come with the next Eclipse in 2023 or something like that. But you can actually use JShell now, and that's on your machine as opposed to over the web. Having a REPL over the web is really cool for teachers. There is probably one of those for everything you ever wanted.
There's a site called REPL.it that has a bunch of them.
Thank you. That's the one that I was trying to remember. Yeah. React Native, okay. I guess not anymore. Maybe I was trying that. Yeah. So you can use almost anything. Actually, there is, if you want, a REPL for C++ that does really tons of cool magic. Yeah. I have no clue what it does. Samples. Well, I think they only have the full thing. You need to do a full program. You can't just type expressions. There is one, I can't remember its name. I always say, oh, this is so cool, and then I never go install it on Linux or something like that. That will do a REPL for C++. REPLs are cool. You want to use REPLs when you're programming. Just because many times you end up having the equivalent of a REPL by having a dumpster project, right? That's already created. You just go and change main or something like that. But a REPL makes it even easier. That is basically all there is to know about data structures. That is all I really need you to know about data structures. For your project, there is a big project right besides assignments, and one of the possibilities is to implement some of these things. In fact, the project is going to be implement for a given problem, implement two things and compare them. But now you have to implement them. But using these kinds of things would be cool. Or any of the 700 algorithms we are going to see. Any other questions about data structures? No? You understand lists, vectors, binary trees, multi-way trees, hash tables, and the idea of maps and sets.
And you use the term vectors for arrays, correct?
Arrays that can grow. This wrapper over an array that can grow.
Array list and stuff.
Array list,
Okay.
yes. The old name for it was vector. There is a vector class in Java, and the name for it in C++ is also vector. I have no clue what the name is in C#. I know that array list.
Yeah.
C# calls maps dictionaries rather than maps. And Python and other languages call them dictionaries. And still other languages call them hashes. Like Perl and Ruby, I think, call them hashes. But yeah, it is. Let me also avoid any more writing of notes and use the fountain of all knowledge, Wikipedia, for a quick review of sorting. Yes, we end at 15, right? Not 45.
15.
There is a couple of things. One of them is the idea of a stable sort. What's a stable sort? If two elements came, right, if there is a tie, right, a stable sort keeps the order that existed. Does that make sense? So if there's two elements with the same sorting key, the one that came first in the array will still be first at the end. For some applications, table sorting is important, but unstable don't care, right? So, what kinds of algorithms do we have for sorting? We have tons and tons of them. There is 2 or 3 that are very popular. Quicksort, bless you, is one of the most popular. Its average running time is n log n, which is about as good as we can do with sorting when we do comparisons. There is a cheating way of saying that we sort faster, but it's not. Yes, it is, but it isn't. So basically, n log n is about as good as we can do. Problem with quicksort is its worst case is n squared. And quicksort doesn't need any extra space. Merge sort does a merge. Actually does tons of merges, right? The traditional merge sort has a problem in that it uses extra memory. Traditionally, you just say, okay, or the most basic merge sort is consider your array as a bunch of arrays of size 1 and merge them by pairs. So merge 0 and 1, 1 and 2, or 2 and 3, right? And so on. And now you have half as many arrays of size 2. And then you do the merge again. And so now you get half as many of size 4 and so on. Each time sorting all of the arrays is order of n. And you do that log of n times. So you end up with n log n. The problem is that the merge requires extra memory. There are different ways where you don't require the extra memory at the cost of sucking more. The other one actually that is very fast is heap sort. We sort of mentioned heaps, right, for priority queues. A heap is a binary tree that's not just balanced, but fully compact, right? So it's completely full, and then the last layer starts from the very left and doesn't have any holes. Does that idea make sense? So it's super compact, and a heap is a binary tree where the top is, in a min heap, the top is smaller than its 2 children. The children, there is no guarantee of how the children are related. Just that, right? The top is smaller than its 2 children. What does that mean? The root is the smallest element in the heap, right? Because it's smaller than its 2 children, then its children will be smaller than its children, and so on. For a priority queue, that means I just need to, I know where the smallest one is, so I can implement my priority queue. And fixing a heap, either when you insert or when you delete, is order of log n. So I just need to, like if I'm removing the root, now I have a hole at the beginning. I just go look, which one of my children is smaller, and that's the one that will become the new root. And then I go try to fix this stuff. Something like that. The book actually explains the algorithm, and it's fairly common. And so a heap sort basically considers the first element a heap of length 1, which is good, and then goes inserting every other element into the heap. So at the end you have a heap, and that's order of n log n. And then just take the first one, fix the heap, takes the first one, fix the heap. Right? And so it is n log n with no extra space. It's actually fairly simple to understand, more or less. Let me make sure that I'm not lying to you. I think selection sort is the one that I think. Yeah. Basically, selection sort is, to me, is the simplest one, right? Find the smallest element, put it at the beginning, right? Then find the smallest of the rest, put it in element number 2, and so on, right? Super simple to implement. What's his problem? N squared, right? If you are required to implement sort in an interview, this is cool because it's super simple, right? Problem is, it kind of sucks in terms of performance. Insertion sort is actually fairly easy to understand, but it's a pain to implement. It is what you do when you have cards in poker, right? Or in poker you have 5 cards, so you don't. But if you have something like Rummy or Canasta or any of those things where you have tons of cards, you pick a new card and just go put it in the right place, right? If you play Uno, right? If you're OCD, you sort by color and then by value within, right? And so when you pick a new card, you just go put it in the right place, right? That is what insertion sort does, except that putting it in the right place when you have a sorted array may be a pain because you need to make space for it, so you need to move everybody else. Does that make sense? And so that makes insertion sort also be n squared. There is a bunch more. The other one that you will always see is bubble sort. And that one is pretty, but other than that, it sucks. On the other hand, it sometimes lets you skip. In bubble sort, you don't just find the smallest element or something like that, but while you are doing it, you go swapping and fixing problems, which is 2 numbers being, right? Just go, if the next one out of order, then I'll swap, and I'll swap. So you end up swapping the same element many times, which is slightly inefficient. On the other hand, you end up many times, if you go through one iteration and you never swapped anything, you know that it's sorted, so you can chop a few runs at the end. It has the incredibly cool thing that looks really cool. It's actually not easy to implement, not easy to understand. It just looks really cool when you animate it. That's, I think, the main reason why it's well known. There is a ton more of them. What do they call this sorting that is by linear sorting? Non-comparison sort, bucket sort. Basically, if you cheat, you can say, oh, I'm going to sort in linear time, not in log n time, right? What's the cheating? Well, here's the deal. Imagine that I'm sorting ints, right? I can do a pass. Imagine that I'm sorting ints between 0 and a million, right? I can sort first by the least significant digit, right? Or the other way around. Which way do they go? I think you have to start by the least significant digit, right? And just go and put the numbers in 10 different arrays, one per digit. So just go to, you go to 0, you go to 1, you go to 2, right? And then do the same, right? Now put them back together and then do the same with the second digit from the right. Put them back together and do the same with the third digit from the right, right? And if I'm putting them together and keeping the order, right? At the end, I'm going to end up with a sorted array. Does that make sense? That is basically bucket sort. So I put them here, and now I do the same for each thing, right? How long does that take? The n, which is the size of my array, and then what else matters?
The range.
The range, the number of digits, right? In a way, if I say, okay, it's numbers from 0 to a million, right? That now becomes a constant, right? So I can say it's in constant time, or so it's just n, right? The way that I tend to look at it is, wait, how do you determine the number of digits, right? Well, unless I have tons of repetitions, it is some version of the logarithm of n, right? If I happen to have 10 million elements, then probably my range is going to be bigger, and so now I'm not going to have 6 digits, I'm going to have 7 or 8, right? So it's basically log n. Heading back. Most books would say, oh, it's linear, but it's actually not terribly useful. There are a couple of variations of this where they actually make it fast enough to compete with something like quicksort or heap sort, but not usually. Again, when you have a chance, you may want to go look at quicksort, just because it's good for interview questions. But other than that, it's good, it works, it's kind of weird, hard to understand. What you do in quicksort, you pick one element and then run the partition algorithm. The partition algorithm goes swapping elements so that at the end, the pivot, the element that you chose, is in its right place in the array. And then all the elements that are lower than it are below, and all the elements that are higher than it are above in the array. And then you just recursively sort the two halves. Does that make sense? Usually, if the pivot you choose is kind of in the middle, then this would take you log n times, right? You need to do that log n times, and you sort it in log n. The partitioning operators is of order n. You don't always guarantee that, so the worst case scenario could get you n squared, or you happen to be really, really unlucky and always choose either the highest or the lowest as the pivot. But usually it doesn't terribly suck. Some other things. How do you find the median? Sorry?
High number algorithm divided by 2.
That's the range, right? Find the highest, find the lowest, and divide by 2. That's the range. That's not the median. What's the median? The center of the list, right? The element in the middle. If you sort them. So what's the easiest way to find the median? Sort them, right? So how long does it take me?
Log in,
N log n, right? To sort and then just go in the middle. There is actually a variation on quicksort that guarantees linear time, because you do something like a quicksort, but you don't have to sort the other half that you don't care about it, right? So there, and that would be kind of an optimization, and then there is a variation where they kind of guarantee that you at least, there is a variation, there's a linear algorithm for finding the median, but for the most part, just say sort it and finding one in the middle, right, would tend to work. If you get on interviews and things like that, there is a linear algorithm. If you want to confuse yourself even more, there are search things that work on vectors. Like, imagine that I have a point in a plane which with x and y, right? Can I sort it? I could sort by x or by y, right? And so when I'm trying to do my searches, sorting doesn't work really well, right? There are multidimensional algorithms where you have a tree and you do it by x and y, rather than just on x or just on y. So that makes, usually they're called spatial, but it's any kind of multi-dimensional things. R trees are the equivalent for trees, and I think grid files are like a hashish table for multidimensional. On this thing, I have not this guy. If you go to the website, I have been collecting some papers. This will probably blow your brain out, which is really cool. Purely functional data structures. It's a thesis, PhD thesis by Chris Okazaki. He also wrote it as a book later. Functional data structures cannot change. Now in Java and stuff, we have this idea of immutable data structures, right? You would think they suck, but the fact is you can store every version. So when you insert, rather than changing your array, you create a new version that has the element inserted. You can reuse a lot of the previous ones. So for many cases, it's actually faster just because of that reuse. And so he's one of the guys who, there's a ton of stuff before, but this thesis is amazing for that stuff. Understanding balancing trees is a lot easier with this stuff. Did I put the other one? Yeah. There is some on more trees, some other ones on hashing and cuckoo hashing and that kind of stuff. Did I put? And I'm terrible. Oh no, there it is. This is an amazing survey on multidimensional access methods, R trees and all of that stuff. So if you are interested in that stuff, go read that kind of stuff. If not, this should be enough knowledge that you should be able to go through the class without any problem. Any questions?
So for a lot of those, we didn't go over the nitty gritty, sit in Java and actually make it. Are we going to be expected to understand it well enough to go home and write some of those, or?
I am expecting you, but this was before the class, to be able to go home, download the paper that explains how it is, and then go implement it in Java. For most of this stuff, what's going to happen is that we are going to say, oh, you can implement a graph with putting the nodes in a map, right? And then going over. So you need to know that a map is order of n squared or order of log n to understand that stuff. But I will not expect you to implement
Okay.
them as a matter of course. This is just so we can talk about, right? You sort, and so that's order of n log n, and then you do this. Or you stuff this stuff, you stuck this stuff in a set, and that's constant time, because it's a hash table or something like that. Does that make sense? And we are going to be using them casually throughout this semester. So I wanted you guys to know this stuff. Also kind of a reminder that that's not the stuff from this class. So at some point in time, which may not be this semester, you probably should get really excited about this stuff and go implement some of these things and go read the nitty-gritty details and things like that. Depending on what else is going on in your life, this may not be the semester where you do that. Hopefully you did it for data structures. But if you didn't, then you probably want to go to it. It's just maybe not right now. Cool. Questions, comments, complaints? No? Then I will give you back 15 minutes of your life.